Okay, I've been a little slow on getting to this, but here we want to show that n squared is less than 2 to the n for n greater than or equal to 5. And we wanted to do this by induction. And, you know, we got started the right way, and then I got stumped for a minute and then realized, you know, once Michael, I think it was, once Michael mentioned something, I went, oh, yeah, of course. Okay. So let's look at this again with induction. We need to show that base case. In this case, we'll want to show it for 5. So 1, n equals 5. We have that 25. Well, actually, let's write down that's n squared. So 5 squared, which is equal to 25, is certainly less than 32, which is equal to 2 to the 5th. So great, we showed it for our base case. Now, for our induction step, we assume that, and often I'll switch to a k plus, k plus, try that again. That k squared is less than 2 to the k for k less than or equal to some n that we're having. And so now what we want to do is show this implies that k plus 1 squared is less than 2 to the k plus 1. Okay, so as I started in class, I usually, with these types of inductions, I just start with that left-hand side there. And in this case, I'm going to square it out, and I'll get k squared plus 2k plus 1. And what we try to do is then section it off into our hypothesis and maybe something else. And so there's the k squared. So I know by my assumption that that's less than 2 to the k, and then plus 2k plus 1. And then, now, as pointed out in class, and I was, my problem in class is I was all of a sudden, for some reason, switching the inequality in my mind. But what we want to do is simply say, oh, this is less than 2 to the k plus 2 to the k. Well, we got to look at that. Because actually, even though you think about a few numbers, it's pretty obvious. Well, we need to show that. But assuming we can show that, then we've got that step, which is, this is now just 2 times 2 to the k, which is 2 to the k plus 1, which is what we needed, right? That's what we needed to show. And so there is our induction step. And, you know, thus, n squared is less than 2 to the n for n greater than or equal to 5. Now, let's look back at this 2k plus 1. So we need, and I'm going to switch to n's here for this. So 2n plus 1, we need that to be less than 2 to the n. Well, that looks a lot like our original problem, and so probably we need induction. And we need this for n greater than or equal to 5 because that's what we were working with. But actually, whoops, quit that. But actually, this is probably true for what? If n equals 3, I get 6 plus 1 is 7 on the left. Oh, I keep hitting something that makes it want to type. let's go back here. Okay. So on the left, I get 7 if n equals 3, and on the right, I get 8. So we need this for n greater than or equal to 5 because that's what we're working with. However, I think what we can do is show it's true for n greater than or equal to 3. So here we have a claim, and that claim is that 2n plus 1 is less than 2 to the n for n greater than or equal to 3. And so again, we'll use induction. And my first step is that base. Okay, I need to show it for n equal 3. And so that 2 times 3 plus 1 is equal to 7, which is strictly less than 8, but that's 2 cubed. So there's my first step. And then the second step is we'll assume 2k plus 1 is less than 2 to the k for k less than or equal to some n. And we need to, hopefully this implies that 2, now here's where you have to be careful with the algebra. The next one is 2 times k plus 1. Then plus 1 is less than 2 to the k plus 1. Okay, so again, well, I'm going to start there. 2k plus 1 plus 1. That is equal to 2k plus 2 plus 1. Now I'm going to swap the 2 and the 1. So this is 2k plus 1 plus 2. And the reason I did the 2k plus 1 is, remember, that's what we're trying to work with here. Our claim is we've got a 2n plus 1. And so using our induction assumption, now I get to say, well, that's 2 to the k, so it's less than 2 to the k, and then plus 2. Now that's 2 to the first. And so now I know that obviously at this point that's less than 2 to the k plus 2 to the k for k greater than or equal to 3. And so now that's 2 times 2 to the k, and that gives me my 2 to the k plus 1. Now you see here, I was able to just use that 2 to the first and 2 to the k. Back here, see, we almost had that. But not exactly. I had 2 times k, and then the plus 1, and so, although it seemed very reasonable to just jump to this next step, wasn't really quite there. Now, so suppose you have to do something like this, for a bigger problem. So thus 2n plus 1 is less than or equal to 2 to the n for n greater than or equal to 3. Okay. So what you would do in a bigger problem or a paper or something like that is actually you would start with something like a lemma. Okay, so here would be lemma 1. And a lemma is really a theorem, but the context is typically, it's a theorem that is used in another theorem. So see, my lemma 1 would be the claim that 2n plus 1, not less than or equal to, I see I put an equal to there, is less than 2 to the n for n greater than or equal to 3. Okay, and I would do my proof as I did up there, you know, blah, 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 blah. Okay, and there's my lemma. And then I would go to my theorem 1 and do the n squared is strictly less than 2 to the n for n greater than or equal to 5. And in my proof, right, you know, I'd have my lines, and then, you know, this line, whatever, you know, that line I needed by lemma 1, and then finish it out, and there would be my proof. Okay, so sometimes, you know, you kind of end up with one proof inside another proof, and this is the way we tend to handle it in mathematics. Is, you know, the preliminary pieces that I needed are lemmas, and then I've got my big theorem. Now, you know, if you have some big results, well, you might have a lemma 1 and a lemma 2, and then theorem 1, and then like a lemma 3 and a lemma 4, and then theorem 2 that uses theorem 1 and the lemmas 3 and 4, you know, because it's that big a proof. Okay, so that was, you know, so there's really two examples of this induction. Okay. Now, though, I want to show you, you can do this without induction. Okay, so just to show, you know, there are usually various ways to get at something. Is, so suppose I want to show n squared is less than 2 to the n, and I would like to show that for, you know, n greater than or equal to 5. Well, actually, I might start that proof out the same way and show, for instance, that, yeah, you know, that 5 squared is less than 2 to the 5th. Oops, 2 to the 5th. Okay, so I'd probably still show that. But now let's look at, think of the function f of x equal x squared over 2 to the x. Okay. Then what we, you know, or at least this is the way I'm thinking about it, because if instead of showing n squared is less than 2 to the n, what if I show n squared over 2 to the n is less than 1, okay, for n greater than or equal to 5. All right, so we'll toss that in. Well, that'll do it, right? That's equivalent. So what I'm going to do is work with this function f of x, x squared over 2 to the x, and, you know, I can get its value at 5, which will be less than 1. But then, if we take the derivative, right, derivative of the top, that's 2x times the thing on the bottom, 2 to the x, and then minus the top times the derivative of the bottom. Let's see, that's 2 to the x times log 2, and then divided by 2 to the x squared, or 2 to the 2x. Now, what I want to do is show that this derivative is negative, right? So if it's negative, I'm starting with, again, you know, 25 over 32. So I'm starting with a number less than 1. And if its derivative of that function is negative, well, it will only be decreasing, so I only get numbers less than 1. And so that's what I want to do, is show that this is negative. Well, for, you know, the bottom is definitely not negative, it's squared. And so I just need to work with the top. And so the numerator and I have a 2 to the x in both parts. So I'll pull that out. And actually, I have an x in both parts. So I'll write x to the x. And then what I have left is 2 minus x times log 2. And so x is greater than 0. 2 to the x is greater than 0. And so the only way, this will be positive or negative is this term here, the 2 minus x over 2. Well, when is it 0 and when is it not? This is just a straight line. And so if we set 2 minus x log 2 equal to 0, that's x is equal to 2 over natural log of 2. Okay, which is a number less than 2. And then if x is greater than this number, okay, x greater than 2 over log 2, well, let's look at what happens. You substitute in, so substitute 2 minus 2 over log 2, actually a number greater than that, and times log 2. So I don't know, a number greater than that. I'll toss an a in there, right? And a is bigger than 1. So right, those cancel out, and you get a 2 times the 1 minus a, but we picked a bigger than 1, and so that's less than 0. So a greater than 1. So I can show the derivative as negative, and if that derivative is negative and I'm starting below 1, then all the numbers are below 1, and that was a calculus proof to show this. So, there are various ways to possibly show something, but definitely induction is a very powerful tool, and so kind of getting a feel for that is a good idea. Okay, so there is our proof and then some of that original question of n squared less than 2 to the n.